Hi, I'm Ben-Yaakov. This presentation is entitled MOSFETs Kelvin Connection. Now, in recent years, we started to see MOSFET with four legs rather than three. So we have four legs here. By the way, there is also a notch here because this is a high voltage device. And then we have like another connection to the source, like two connections to the source. And in this presentation, I'm going to first of all explain why we would like to have it, and then some problems that might arise in some situation and how to solve them. So what is the Kelvin connection? Let's start with that. If we want to measure, say, the resistance of a resistor here, we can inject a current and then measure the voltage across these terminals. The problem is that if the resistance is very low, then the interconnection can contribute quite a bit to the resistance. So in this case, you're going to get an error. So the idea of a Kelvin connection is that you're injecting a current and then you measure the voltage just across the resistance itself rather than an interconnection. Okay? So a current sensing resistor might have in fact four terminals, two for the current passing through it, and then two for sensing the voltage. Now, the Kelvin connection comes from the Kelvin bridge, which is a rather involved configuration, which is meant to measure by a bridge type of a testing the resistance of an unknown resistance, if you know the reference resistance, by a bridge which is sort of balanced. And it can be shown, I'm not going into it of course, that in this type of a connection, you can get rid of these external resistances and you just measure this resistor, and the end relationship is that the resistance is the ratio between these two branches, the resistance of these two branches, times the reference resistance, if the ratio here is equal to the ratio here. So this is the Kelvin bridge connection. Let's go back, however, to the MOSFET. Now, in a regular drive of a MOSFET, we have the gate, we have the source, we have the drain, and here is the driver. Might have an impedance in between. I'm showing just a simple resistor. Now, the problem is that all these lines do have inductances. So when a current is passing through them, and especially here, very high current, the drain to source, then you do have voltage drops here, and consequently, the gate to source voltage actually seen by the transistor is different from the drive. You have these two additional sources which are noise, and this could be very harmful if the level of the noise is, of course, high, and you'll be, say, passing the threshold back and forth. This could be very harmful. So the Kelvin connection comes to the rescue, and the idea is the following. There is an internal connection between this Kelvin terminal to the chip itself, not to the wire of the source, but rather to the die itself. Okay? By this, you eliminate the voltage drop of this line here, which is very important because this bonding line might have quite a bit of a inductance, and of course the interconnection here, not to mention the PCB, etc. So you are of course left with some inductance on the Kelvin line itself, but then the current here is just the drive and not the main current going through the transistor. So this is the idea of the Kelvin connection. It requires, of course, a isolated power supply for the driver, which you would like to have anyhow in the case of high current, and of course all this is related to high current, high power circuits. So you need a isolated power supply which is supplying this driver. However, there are some problems here that I'm going to address. The first one is when paralleling transistor. To get higher current, higher power, you usually parallel transistor. So in this case, the simple connection will be you have a driver, and then the low side will be connected to the Kelvin connection. And then you have of course, the gate signal coming here and then coming here. Now there is a problem here because voltage drop here, you have noise here, and all this will cause a circulating current here in between these two branches here, which are in parallel. which again will corrupt the signal that the gate to source is seeing here and the gate to source is seeing here. So you are losing sort of the advantage of the Kelvin connection. Now, a possible remedy for this is to add these resistors. Well, the idea is that by this resistor, you reduce the circulating current, and the voltage drop here on this line, which usually is going to be a fairly small, thin wire, so it's going to be very heavy copper. The voltage drop on it will be much lower, so therefore the gate to source voltages will have less noise on them. Now, when you do this, you increase the resistance of the loop here of the drive to the gate, and I'm showing it here in a more intuitive way. It's like adding your resistance here. So obviously you'll have to compensate for this additional resistance by reducing these resistances here so that the total turn on and turn off resistance would be the one that you would like to have. This problem also appears in the case that you have a bridge and then you have two low side transistors. They may also be parallel to other transistors, but let's just talk about one transistor on each side. Now here again, you'd like to use the same power supply for the two sides because obviously this is the same line, the same potential here for these two. But again, without this resistor, you may have quite a bit of a circulating current here. So you better put some resistance here in between. And again, you have to adjust for it in the actual drive side. So this brings me to the end of this very short presentation. I hope you find it of interest. Thank you very much.